Welcome to lesson 10-2 for Algebra 1. This lesson is entitled Simplifying Radicals. It's been a long time since we talked about math. I understand if you guys have forgotten some of this stuff, but we're going to go ahead and pick up where we last left off. And lesson 10-2 is going to talk about how to simplify radicals. So before we can talk about how to simplify a radical, we have to remind ourselves, well, what exactly is a radical? Well, a radical expression is any expression that has a radical symbol. This one in particular is called a square root symbol, which you're probably familiar with those. But we need to talk about how to simplify these things, what makes them simplified and what makes them not so simplified. So here are some examples of some simplified radicals and some not simplified radicals. And there are three main rules that tells us whether or not they are simplified. All right, the first rule is the radicand. We should probably take a step back, and we should probably look a little deeper into what a radical is. So yes, before you ask, you are expected to take notes, and this is probably something that you should put in your notebook. All right, let's go ahead and explore the different parts of a radical. There are actually three parts of a radical. Two of them are shown here. One of them is kind of hidden. The first thing that is an indicator that we have a radical is the radical symbol. Oftentimes we call this a square root, but technically it doesn't have to be a square root. We're just going to call this the radical symbol for now. The second part of a radical is a number on the inside of the radical symbol, and this is called the radicand. Radicand. And the third part is the number that is actually hidden up here, and right now we're going to go ahead and make this a 2, right? But this number is called the index. And it does not have to be a 2. This is a 2 because we're talking about a square root. But if I change this to a 3, then this becomes a cubed root and the index can change. So all three parts, the radical symbol, the radicand, and the index, they make up the total radical. All right, so these are the three things that we should probably pay attention to before we start looking deeper into what a radical is. So let's look back at these three rules that tell us whether or not we simplified a radical. The first rule is the radicand has no perfect square factors other than 1. We'll come back to that one. That's probably the more complicated of all three rules to understand. We'll come back to that one. Rule number 2, the radicand contains no fractions. If you look at this example right here, on the inside of our radical symbol there's a fraction. So that means it's not so simplified. All right, so this is not simplified, whereas this one is perfectly fine. Rule 3, no radicals appear in the denominator of a fraction. In this case right here, square root 7 is in our denominator, so this is not simplified. All right, looking over here, we do have a fraction, but notice the radical symbol is in the numerator, and that's perfectly fine. We're allowed to have a radical in the numerator, not in the denominator. All right, so let's go ahead and go back and look at that first rule. The radicand has no perfect square factors other than 1. Here's that example, and this is 3 square root 12, and in the book it says 3 square root 12 is not simplified. Why not? Well, because there is a perfect square factor within 12. If I try to do a factor tree for 12, I can say 12 is 1 times 12 or 2 times 6, but it's also 4 times 3. And 4 is a perfect square. And that means that this is not simplified. I can say that 3 times square root of 12 is the same thing as 3 times the square root of 4 times the square root of 3. Right? And because the square root of 4 can be simplified, we must simplify it. The square root of 4 is 2. So this is the same thing as 6 square root 3. Now if you take a calculator out and type this into a calculator, if you multiply 3 times the square root of 12, you would get the same thing as 6 times the square root of 3. And that's one way that you can check to make sure that you are simplifying these correctly. The main thing that we're looking for is if we look at our radicand, the only perfect square factor it's allowed to have is 1. If it has another perfect square factor somewhere in there, we have to keep going. We have to simplify further. This brings us to the multiplication property of square roots, which says if you ever have a radicand that has factors, you are allowed to split it up into the multiplication of those two factors with two square root symbols. In this case, 48 is the same thing as 16 times 3. So the square root of 48 is the same thing as the square root of 16 times the square root of 3. Now 16 is a perfect square. 4 times 4 equals 16. So that just goes ahead and turns into a regular 4, square root 3. Let's look at problem number 1 in your book that talks about simplifying the square root of 160. Now the square root of 160 is the same thing as the square root of 16 times the square root of 10. 16 times 10 is 160. And the square root of 16 is the same thing as 4. Now, does 10 have any perfect square factors in it? If I do a factor tree for 10, it's 2 times 5, and neither of those are perfect squares. So we just leave it like that, and that is our simplified answer. So this is one way that we can try to simplify square roots by trying to think of what perfect square factors are there. There's another way that I'm going to teach you how to do that's very helpful for whenever you have variables. But for now, this is a good way to go about things if you're pretty confident with your perfect squares. Got it? Question number 1 asks, what is the simplified form of the square root of 72? So what we need to do is we need to think of what is a possible perfect square that's a factor of 72. Well, let me think. What are my factors of 72? Well, 72 is an even number, so it's at least divisible by 2. But I also know that 72 is divisible by 9 as well. Right? 9 times 8 is 72. And hey, 8 has a perfect square factor in it as well, which is the same thing as 4 times 2. So my perfect square factors are 9 and 4. So that means that the square root of 72 is the same thing as square root of 9 times the square root of 4 times the square root of 2. 9 times 9, or 3 times 3 is 9. 2 times 2 is 4. And square root of 2 is square root of 2. That can't go any lower. So that means that when I multiply these out, my final answer is 6 square root 2. You might have noticed, or maybe you thought, perfect square factors of 72, I know 36 is a perfect square factor, 36 times 2, and I would have got 6 square root 2 in either way. So there's a lot of ways that we can do this, but we want to make sure we pick a way that's easiest for us to get to the correct solution. Okay, problem 2. Things get a little bit more difficult because now we're introduced to this idea that we're allowed to have variables inside a radicand. How does that change? How do we simplify? Because thinking of a perfect square for 54 might be able to get it done, but n to the power 7, that's kind of weird. So I'm going to go ahead and show you a different way to think about this. This is called the ticket method, and I have a little illustration to kind of help us understand what the ticket method is. Now let's say that this is you, and you are going at the carnival. Again, I even gave you a little face mask as a sign of the times of what we're dealing with right now. You're at the carnival, and you notice that the ride you want to go on, it costs 2 tickets per ride. And in your wallet, you have exactly 2 tickets. How many times could you ride the ride? Well, if it costs 2 tickets and you have 2 tickets, you can ride the ride exactly 1 time. 1 time. Make sense? Alright, now we're going to apply that same idea to the concept of square roots. Alright, if we thought of our radical symbol as a carnival, because you know carnivals can be rad, we have a radical symbol, right? Then I can say that everything on the inside of the radicand is how many tickets you have. This exponent right here is how many tickets you have, and the index, that invisible number, that number 2 that we just kind of assume is there, that's the cost. if X has 2 tickets and it costs 2 tickets, how many times can he ride the ride? He can ride the ride 1 time. The square root of x squared is the same thing as 1x. In fact, you can even say that these two exponents, the index and the exponent, they actually cancel each other out. Let's do the same thing over here. If the index is 2 because this is a square root and it costs 2 tickets to ride the ride, and m has 5 tickets, how many times can he ride the ride? Well, if he has 5 tickets, he can ride the ride twice, right? Because he would use 4 tickets on the ride and he would have 1 left over. And that leftover is just going to be put inside of our, what is going on there? All right. The leftover is going to be put inside of our radicand. So this is an example of the ticket method, where we ask ourselves, how many tickets do we have? How many tickets does it cost? This guy can ride the ride, and this guy stays home. In the case of the simplified form of the square root of 54 n to the 7th power, what we can do is we can use our factor tree to figure out what are the factors of 54. I could say this is the same thing as 9 times 6, which is the same thing as 3 times 3, which is the same thing as 3 times 2. N to the power of 7 is the same thing as n to the power of 7. When I combine all of these, I end up getting 2 times 3 cubed times n to the power of 7. I have 1, 2, 3 threes, and I have 1, 2, and 7 n's. That means that if I'm going to use a ticket method with an index of 2, because it's a square root, all square roots have an index of 2, I would just have to go ahead and apply my ticket method to this problem. Now, if 2 has 1 ticket, how many times can 2 ride the ride? Well, he can't ride the ride. It costs 2 tickets to ride the ride. He only has 1, so 2 is going to stay home. 3 has 3 tickets, and it costs 2 tickets to ride the ride. So that means that 3 can ride 1 time with 1 ticket left over. N has 7 tickets, and it costs 2 tickets to ride the ride. So N can ride 3 times and use 6 tickets with 1 left over. So our final answer is going to be 3 times n cubed square root of 6n. Here's an example for got it question number 2 that kind of deals with the same thing. This time we have a negative m already outside in front, ready to ride the ride, so we don't have to worry about him. We're only going to worry about simplifying the inside of the radicand. 80 is the same thing as, let's say, 8 times 10. 8 is the same thing as 4 times 2, which is the same thing as 2 times 2. And 10 is the same thing as 2 times 5. If I bring all these down, I figure out that there are 1, 2, 3, 4 2's. So this is the same thing as negative m square root of 2 to the 4th power times 5. There's 1 5, and there are 9 m's. The radicand is still going to be 2, so we can go ahead and start using our ticket method from here. Alright, so whenever I am trying to simplify these things, I like to go ahead and leave myself just a little bit of space. I like to start by putting my square root over here and leaving some space on this side just in case there are numbers that have to go in front and in case there's numbers that have to go on the inside. Alright, I know that I have negative m already waiting in line. So I'm going to go ahead and put this here. Actually, let's take a step back. I'm going to go ahead and put the negative sign in front. I'm going to put an m towards the back. Generally, whenever we're doing these things, we like to put our numbers in the front and our variables in the back. So I went ahead and used this guy. Boom, boom. Already moved in. All right. 2 to the power of 4. All right, we have 2 has 4 tickets, and it costs 2 tickets to ride the ride. So that means that 2 can ride the ride twice. With how many tickets left over? Well, he used all of his tickets, so there are none left over. 5 has 1 ticket, and it costs 2 tickets to ride the ride. He doesn't have enough tickets, so 5 is going to stay back, and his 1 ticket's going to stay back. M has 9 tickets, and it costs 2 tickets to ride the ride. So that means that M can ride the ride, what is that, 4 more times. He uses 8 tickets, so he has 1 left over. And if I multiply all of these numbers in front together, I end up getting negative 2 times 2 times 2 times 2 is 16. M to the 5th power, because m to the 4th times m to the 1st power is m to the 5th. Square root of 5m is supposed to be an m. Cool. All right. All right, what if we try to multiply 2 radicals together? Like in this case, for problem number 3, we have 2 square root 7t times 3 square root 14t squared. Well, it's actually kind of easy. It works very much like you think you would. You multiply the numbers on the outside together, and the numbers on the inside can actually be combined as well. So let's go ahead and take a look at this. All right, so for this problem, I went ahead and rewrote it. I have 2 square root 7t times 3 square root 14t squared. Now, I have 2 numbers on the outside, 2 coefficients, so I can just go ahead and say this is the same thing as 2 times 3. And on the inside, I have 7t times 14t squared. All right, now 2 times 3 is the same thing as 6, so that's not that big of a deal. And what I would do is I would kind of start grouping these together. If I know that 14 is the same thing as 2 times 7, then 7 times 2 times 7 is the same thing as 2 with 2 7s. And I have 1t and 2 more t's, so this is going to be t cubed. Now, our index, because this is a square root, is still just going to be 2. So it takes 2 tickets to ride the ride. Let's go ahead and start pulling the riders out in front where they're supposed to. So I'm going to go ahead and start with an empty square root. And I have a 6 already in front of the line. Already there, got there early. Now, if it takes 2 tickets to ride the ride and there's only 1, 2, he doesn't have enough tickets, so he's just going to stay back. Boom. 7 has 2 tickets exactly, so he can ride the ride 1 time with no tickets left over. And T has 3 tickets, and it costs 2 tickets to ride the ride. So that means that he can ride the ride once with 1 left over. You simplify all of these together. 6 times 7 times t is going to be 42t square root 2t. So we're just using our ticket method. We're combining or multiplying the numbers on the outside, multiplying the numbers on the inside, and then from there, we're doing our ticket method. Let's take a look at Got It Question Part B. Got It Question 3, Part B. All right, we're asked to go ahead and simplify these two together. Notice there's no number on the outside, so we don't have to worry about that. We just want to go ahead and combine the numbers on the inside all into one big happy radical. So we're going to have a 2. We're going to have a 9, which is the same thing as 3 times 3. And we're going to have 1, 2, 3, 4 a's all together. The index is 2 again because it's a square root. All square roots have an index of 2. It costs 2 tickets to ride the ride, so empty square root. 2 can't ride the ride, stays home. 3 can ride the ride 1 time with no tickets left over. And A can ride the ride 2 times if it has 4 tickets and it costs 2 tickets to ride the ride with none left over. So it looks like our answer was 3a squared square root 2. We're going to skip question number 4 and we're going to go right to the division property of square roots, which says that if you ever have a fraction on the inside of a square root, if you remember from the 3 rules we learned at the beginning of the lesson, this is one of the no-nos. You're not allowed to have a fraction on the inside of a square root. But you are allowed to split it up into 2 different fractions. If I have a fraction with 2 different square roots, if I have a square root with a fraction on the inside, I can split this up and I can find out the square root of 36, which simplifies to be 6, and the square root of 49, which simplifies to be 7. So if I ever have a fraction on the inside of my square root, one possible thing I could do is I could actually split it up into 2. Right? It might not work every single time. In this case, both of those are perfect squares, so you can simplify. And if you're left with something that's not a perfect square, you might have to use a little mathematical wizardry to get your way out of that one, but it works. So let's go ahead and look at this example. The square root is 64 over 49. I can split this up into 2 different square roots. 64 is the same, square root of 64 is the same thing as 8. The square root of 49 is the same thing as 7, and this would be our simplified answer. Looking at part B, neither 8 nor 50 are perfect squares. But if you cross cancel, if you reduce and divide both of them by 2, 8 divided by 2 is 4. 50 divided by 2 is 25. And even if you cross cancel the x's, you end up with a perfect square here. The square root of 4 is 2. The square root of x squared is x. And the square root of 25 is 5. And this one's simplified nice and easily. Got it. Question number 5 has a couple of interesting problems. The first one's not too bad. If I want to simplify the square root of 144 over 9, I can split it up into 2 different square roots. The square root of 144 over the square root of 9. The square root of 144 is 12. The square root of 9 is 3. And 12 divided by 3 is 4. Simplify as low as you can go. All right, easy enough? Cool. Looking at part B, I have some variables in there. I do note that the 1a on top can cross cancel with one of the a's on bottom, and I can rewrite this as the square root of 36 over 4a squared. There was 1a on the top, and there were 3 a's on the bottom denominator, and I'm left with 2 in the denominator. Now, why is that so special? Because now I can split it up into 2 perfect squares. The square root of 36 over the square root of 4a squared, which is the same thing as 6 over 2a. Now, these can cross cancel, become a 1 and a 3, and I end up with 3 over a as my final answer. I want to try to keep my variables positive. Looking at this one, I know that nothing really cross cancels, but I can do the square root of 25, the square root of y cubed, and the square root of z squared. The square root of 25 is 5. The square root of y cubed, ticket method. If I have a 2 as my index, then I can go ahead and say that I'm going to have one y that can ride the ride, one y that stays home, and it looks like we have one z that can ride the ride. Nothing cross cancels, and this is our answer. Now, there's nothing else that we can do because it's perfectly fine to have a square root in our numerator, not in our denominator. So this is a good answer for us to get. All right, very last thing for us to talk about in this very long lesson dealing with radicals is how to rationalize denominators. Now what that means is we want to turn our denominator to a rational number. Right now it's irrational. The square root of 7, if you type this in a calculator, would just go on infinitely forever without repeating itself in any pattern. That makes it an irrational number. We're not allowed to have irrational numbers in our denominator. So we need to come up with a process to get rid of these things. Alright, so you guys ready for the last example for us to do? Here it goes. Whenever you're trying to rationalize a denominator, you will always multiply both the top and the bottom by the denominator. In this case, I have a denominator of the square root of 7, so I'm going to multiply it by the square root of 7 over the square root of 7. Why is that okay? Well, square root of 7 divided by the square root of 7 is the same thing as 1. Multiplying it by 1 doesn't change the value, but it might change the way that it looks. Mathematical wizardry. What happens when we multiply the square root of 7 times the square root of 7? That gives us the square root of 49, which is the same thing as, you guessed it, 7. That must be a coincidence. Man, I don't know. Alright, square root of 3 times the square root of 7 is the same thing as the square root of 21. That can't go any lower, so our final answer right here would be the square root of 21 over 7. Now, why is this okay? You're allowed to have a square root in the numerator, not in the denominator. So was this really a coincidence? The fact that when we multiply a square root times itself, we got the radicand. No, actually that happens every single time. And that's actually what we want. We need that to happen. There's no way these problems would work if they didn't work that way. So let's go ahead and try it over here on this very last example. The square root of 7 over the square root of 8n. I have to multiply it by the denominator over itself. Now, when I multiply these, the square root of 8n times the square root of 8n is just going to be 8n. And we're going to have the square root of 7 times 8n is going to be 56n. Now we need to go ahead and simplify this top part. What is the square root of 56n? Well, if I went ahead and did like a little factor tree, 56 is the same thing as, let's just say, 4 and 14, which is nice because this gives us 2 square root 14n over 8n. Cross cancel, and I get the square root of 14n over 4n. Now, can this n and this n cross cancel? No. Why not? Well, because this n is inside the square root and this guy isn't. This guy, they're two technically different degrees, but we don't need to worry about that right now. Well, that's it for this lesson. I know it was a long lesson. Thank you for hanging in there. A lot of good stuff in this one. Good luck with your homework, and if you have any questions, just come to me. See ya.